Hi, everyone. Just want to make sure if my soothing voice can be heard by everyone and that the slides are visible.
The slides are visible.
Yeah.
And it's thumbs up.
For hearing my soothing voice as well.
Mm-hmm.
Thanks. So yeah, I missed the introduction earlier on, so I don't know what nonsense was told about me. So I will just quickly introduce myself again. I'm Paul van Staden. I'm a failed stand-up comedian pretending to be a lecturer at University of Pretoria. And last few years, I have been sitting down behind screens more than I was standing in front of audiences, even COVID and so forth. So actually today's again strange for me because I'm now sitting and presenting instead of walking around. I don't have all the time a snake around my neck. I don't like ties and I don't like Pythons and I don't like Python that much. But yeah, we are going to code in Python today a little bit. But yeah, that is about as much as I like Pythons as you can see there around my neck. And that's an old picture. I'm much older than that now. I mean, that picture must be more than 20 years old. So yeah. In the next part, we're going to focus on probability and then categorical data. And there's so much that I can bombard you with in terms of categorical data, but it's definitely not the idea of Rene or me to scare you away from statistics. And for that reason, I'm going to use simple example that is hopefully enjoyable examples to illustrate concepts. And I believe less is more. So instead of doing a few multiple hypothesis testing examples, I will be focusing on what I would assume within categorical data, the most important hypothesis test that you want to do testing for independence. And I will keep the example simple and straightforward. And then I do have an exercise where the data is a little bit more complicated, but not really that much. So the example we're going to have a look at is inspired by, on the one hand, Jerusalem, that I don't know which year it was released, but I know it was during COVID. During COVID, I had to develop a first-year statistics module that is presented at the University of Pretoria. So that module was born during COVID at home. Now I need to raise that child at the University of Pretoria on campus, which is an interesting experience. We started off with like 200 students the first year, and by now we have more than 1,000 students taking the module annually. So it's a statistics module that's presented for first year students, introductory statistics, but they do everything learning coding. It's not the typical first year statistics module where calculators get used. We don't use calculators at all. Everything has to be done through coding. For that module, we actually use R, but yeah, for today, we're going to do coding in Python. So I must be honest, I'm far more familiar using R or even SAS than Python. I'm definitely not a Python expert. I have to constantly ask Dr. Google what to do in Python, but I also have to ask Dr. Google what to do in R. So it might not be within your, where you are studying allowed, but in the modules that I present, I allowed students to Google all the time. Googling is allowed. It is, assessments are not open book, but open resource. So students are allowed to Google, and if they want to waste their time on ChatGPT, they're more than welcome to do so as well. So this example is taken from a book which you must please avoid unless you are shocked easily. It's actually a book used in social sciences, discovering statistics using SPSS. SPSS is a statistics software package which is not available on my laptop. I don't have that software package installed on my computer. I've never used it. I think there's also an R version of the book available that will be newer than 2009. There's no Python version available. And the official title of the book is Discovering Statistics Using then either SPSS or R. If you go to the inner pages, the front cover is repeated, and then in brackets, those words are put there, and sex, and drugs, and rock and roll. And the author field is not lying. He uses all of that and more shocking to explain statistical concepts. I've taken from the book one of the examples that will hopefully not get me into more trouble than I'm already in. There's nothing shocking about this example, except if you are a cat. I've adapted it. I've changed the data, for example, a little bit. So if you do get a hold of the textbook, then you find this example, you will see that I took the liberty of changing the gender from, I think in the book it is a male that tortured the cats. Here, for some reason, it's a female. But also I've changed the numbers. So I can't remember the exact number of cats that were mistreated in the textbook. Here I've changed it on purpose to 80 because I want to show something very specifically. So I made it a nice round number, 80 cats. So for some strange reason, this researcher interested in whether animals could be trained to line dance. And I cannot dance at all, whether it is in line or whether it is non-linear. We will later get to linear regression. I cannot dance, to the horror of my Argentine wife, who loves to tango and all kinds of strange dances. I cannot. I know in Jerusalem, there is specific dance moves that needs to be performed when you do dance to Jerusalem. I cannot do that. But this researcher wasn't bothered whether I could do it or not. She wanted to know whether cats could be trained to line dance. And she wanted to actually see whether the type of reward that's given to cats will have an impact on their ability to learn to dance. And she decided on either giving the cats food and no love, or giving them affection without feeding them as a reward. So in that book from which I took it, they used the word affection, but affection is too long to type every time, especially when I got to the table. It made that the column width had to be too wide. So I just changed affection to love. I assume for a cat that means basically the same. And in the case of these poor cats that received love or affection, shame, they starved. They were giving no food in a loving way, if that is possible. And apparently this happened for a whole week. And then at the end of the week, after a lot of training and a lot of eating or not, or a lot of affection or not, she counted how many cats could line dance and how many could not. So we don't have this information now available in terms of each and every of the 80 cats can dance or not, or given food or love. We are giving the information in a summary form. And the summary form is known as a frequency table, or then also it is named a contingency table, where for this table, it's a 2x2 table. We have two variables that we are looking at, or we're going to first refer to it as the two events that we are looking at. Later, we will rather talk about variables. So the first is in terms of the reward, which has two levels. So when we say 2x2, there are two rows, two levels, two categories that we have. The reward is either food or love. And then in terms of the ability to learn to line dance at the end of the week, it's a yes or a no. In total, we have 80 cats. And as I said, I've on purpose changed it. It doesn't really have to be that way, but it will make it easier for us later on when we get to a test for independence. I on purpose made it now 40 of the cats received food as a reward and 40 cats received love. There's no reason why it really has to be equal, the two subsamples, 40 each. I would suggest, of course, if this is now an experiment that you are planning to repeat, that you try and keep it balanced. So it's not that I would give, try and be cheap and just buy food for 5 cats and then have 75 cats just receiving love. You want to have it sort of balanced. So you would want to have these totals reasonably close to each other. But yeah, I've made it on purpose exactly 40 and 40. So these are my row totals. And then in terms of the column totals, out of the 80 cats, a whopping 44 of them, which is quite a lot, they actually did learn to line dance. And 36, the remaining 36, unfortunately, could not learn to line dance. So those are the column totals. And then inside the table, that is where we have now a combination of the two events. So there's 28 cats out of the 80 receiving food and able to line dance. Out of those 40 cats there, 28 yes, and therefore 12 no. So notice these two cells add up to the 40. Likewise, 16 plus 24 will also give me the 40 there. And if I sum the columns, 28 plus 16 gives me 44, and 12 plus 24 gives me 36. So adding up those four cells will give me 80. So each and every one of the 80 cats represented in one of these four inner cells there. We will be then randomly selecting a cat. So when probabilities get calculated, this is typically how things get framed, that you have your sample of 80 cats, but let's suppose we randomly select a cat and we want to then work out probabilities in terms of this randomly selected cat. So we have two events that we define. We firstly define an event A, which is that the cat could line dance. So event A will be for the first column. And then the second event is in terms of the rewards. We're going to make that the cat was given food as reward. So that is the first row. Immediately, we can then also have the complement of these events. So we refer in probability theory to a complement. So either the cat could line dance or not. There's no other alternative. So the A complement would be for us, cats could not line dance after 1 week. And likewise, B complement would be that the cat was given love as reward. So that would be for the second row. So we have an A complement and a B complement as well. Those are the complement of the two events defined here. Now you must please stop me, because I will just continue and continue and then even skip lunch. Please stop me if there are anything that's not clear.
So far, there's no questions.
Okay. So yeah, we can then calculate probabilities. Just I need to. We can calculate probabilities. So we can start off very easily for our randomly selected cat. What is the probability that that cat now could line dance? Well, it's one of the 80 cats that we've randomly selected. We now want to know what is the probability that the cat could line dance. So from our table, that's quite straightforward to calculate. It would be 44 out of 80. And I'm not going to do that with each and every one that we have here, but of course, go into Python. Later, we will get to this code, so don't worry about the code yet. But I could now, of course, go on here and say 44 divided by 80. And if I run that, I will get the 0.55 probability calculated. So you can use Python as a calculator. So I do not know why I have first-year students that are still, they need their calculator, even when they have an exam in a computer lab. May they please have their calculator as well. I don't know why, but yeah. I don't possess a calculator anymore. Let me get back here. So that is straightforward to do. The probability of A, 44 out of 80. So probability that my randomly selected cat could line dance, 0.55. What is the probability that this cat could not line dance? Well, it's 1 minus 0.55 or 0.45. It is basically, there are 36 that couldn't line dance out of the 80. So 36 out of 80 gives 0.45. Similarly, we could ask, what is the probability that the cat's reward was food? Well, I've, on my example, made it 40 and 40. Half of the cats basically received food. And therefore, the probability that this randomly selected cat was starving not to death, but to hoping the end of the week would come soon, receiving far too much love and nothing to eat. Well, that probability is also a half. It's the probability of B complement, which is 1 minus probability of B. I didn't retype that now here, but yeah, straightforward to calculate. These are basic probabilities to calculate. We can complicate things a little bit more by phrasing questions like these. And these two questions look very similar. In fact, they are similar, the questions. In these two sentences, one word differ between the two sentences. The first one says, what is the probability that the cat could line dance and that the cat's reward was food? I should have actually maybe changed that font from boring Times New Roman to something more exotic and find another color except for deep pink, some other bright color to highlight it. That is the word and, that in the second bullet was changed to what is the probability that the cat could line dance given that the cat's reward was food. These two questions seem very similar, but they actually ask vastly different things for us. The first one is where we want to know what is the probability that A and B occurred. A being that the cat could line dance and B that this cat's reward was food. So to get this probability, if we go to our table, we don't go to a column total or row total now as what we did here to calculate these probabilities. For this, we go to the inner cell. We go where we have the intercept. Line dance, yes, and the intercept with food, so that 28. And then importantly, it's 28 out of 80. In total, we have 80 cats that we are looking at. So it is 28 out of 80, or then 0.35. So this is the symbol in probability theory indicating intercept or and. So if we read this, it's probability A and B. What is the probability that the cat could line dance given that the cat's reward was food? In probability theory, there is a conditional probability rule. This is now a conditional probability. That word given is the magical word telling you, I want a conditional probability that I need to calculate. What is given? It's given that the cat's reward was food. So given that B has taken place. What is the probability of A? To write that down in the correct notation is probability of A, and that vertical little line stands for given B. So this is A given B. And then our rule is that if we want to calculate this probability, the formula is that we say the probability of A and B, we take the intercept between the two events, and you divide by the probability that is given. So probability A and B divided by probability of B. And this we already calculated as 28 out of 80, or 0.35. Probability of B is a half. We get that there. So the answer is 0.7 if we simplify here. But we can also get this directly from the table. If you did not want to use the formula, or you could remember the formula, we could calculate this directly from the contingency table. If we scroll back up, we want to know, given that B has taken place, so given that it was now food, so we don't focus on 80 cats, we are focusing now just on these 40 cats. What is the probability that the cat could line dance, given food was the reward? So it's 28, not divided by 80, but 28 divided by 40. And it again gives us the probability of 0.7. Any questions there, Rene?
There's no questions on the Slack, and I also don't see any questions.
Okay,
on Zoom.
For those that want to ask them. Okay. So, okay. Both of these are important probabilities. We will get at some stage this morning or afternoon to probabilities that are slightly more complicated than what we are doing here. So it's important that you do understand what happens here. That this is the probability of both events occurring. This is the probability of the one event occurring, given that we know the other has occurred. So given that the cat's reward was food, what is the probability that the cat could line dance? And of course, in a similar way, you could work out the probability of A complement and B, or the probability of A complement given B, or the probability of A given B complement. You could change the A and the B in other ways. You don't have to be A and B. It could be A complement, B complement, and so forth, depending, of course, what is asked in the little word problem. Now, the next question becomes an interesting question. Based on what we've observed, can we conclude that learning to line dance cats depend now on the type of reward? Is there a dependency between these two events, learning to line dance and then the type of reward? Well, we've seen that the probability that a cat learns to line dance is 0.55. Given that the cat is given food and no love, so given B, the probability of A is not 0.55, but 0.7, 28 out of 40. So now that is 44 out of the total of 80. Here it's given B, so it's out of 40, 28 out of 40, it's 0.7. Because these probabilities are not equal, it tells us, well, it does matter what these cats were given, whether it was love or food, whether it was food B or B complement love. For independence, to have independence between events, the probability of A must be equal to the probability of A given B. This is not happening in our example. Therefore, our conclusion is that A and B are not independent events. So in effect, what we've now shown here, that learning to line dance does depend on the type of reward. It does matter what you do with your cats, or if it's not your cats and other people's cats that you are torturing, well, it does matter what you do with those cats in order to get them to learn to line dance. Type of award. I say I have here the word award. It's interesting. Actually, I think it should be a reward. Yeah, sorry, that's a typo. I think there's a difference between an award and a reward. Yeah, it's not type of award, but that must be type of reward. So sorry for that. Yeah, no cats were given any awards for dancing ability. Yeah, all of them were given a reward to get them to dance, and that was either food or love. Yeah, sorry for that. Student type slides 3 o'clock in the morning of Sunday evening. This was not done this morning. 3 o'clock. It's done over the weekend. Okay, before I move on, any questions about independence or anything else that I've explained here?
There's nothing in the chat. There's nothing on Slack. Maybe I can just give them a minute to.
Okay, yeah, I will keep it. While I wait before, if there are questions, what I want to point out, this is now a very simple example. We are looking at two events, A and B. Okay, there's A complement and B complement, but yeah, two events. It's a 2 by 2 table. Because it is only 2 levels within each category there. So the word has food, love, or their line dancing, yes or no. So 2 levels there, 2 levels there. To detect for independence, we can do it as it was done here. Probability of A not equal to probability of A given B, so we do not have independence. This, what we've done here, would not work if any of the 2 variables, or then what we are looking at here, had more than 2 levels. If, for example, apart from food and love, there was a 3rd type of reward given, water, although I think water will constitute food, but I'm trying to make it easy, say food, love, or water, then you cannot do it as we've done it. It would not be possible to check for independence easily the way that we've just done it. Also, I've based my decision here of independence on this particular sample here. But of course, if I were to look at a different set of NITheCS, then these frequencies might change. Therefore, we actually want to use a formal hypothesis test if we want to test for independence. And that's what we're going to get to next. So if there are no questions, then we will move on to the hypothesis test.
There was a comment, all good.
All good. Okay. Well, yeah, because we are not cats. So everything is, of course, good for us. Okay. So next up, we're going to move over to testing for independence now, which is a very important hypothesis test when working with categorical data. So if you have data that is in terms of categories, typically you want to know whether your variables are independent or dependent. So I've repeated the table here that we had before, and I've added here in brackets in red some extra information, which I will soon say where that comes from and what it's telling us. So it's apart from that, it's the same information. Line dance is yes or no. A reward is food or love. And it is still a two-way table and a 2x2 contingency table in that we have 2 levels here and also 2 levels there. So we didn't change any of the frequencies, or we sometimes refer to these as counts. We counted how many were given food and good line downs and found 28 out of 80. So I didn't. So in blue, that is actually referred to as the observed counts. So that is observed. Oh, sorry. We will soon see it's there typed as well. 12 is observed, 16 is observed, 24 is observed. Now, if we have independence, then we should have that, given that we had 40 cats there and 40 cats there, so half of the cats given food, half of the cats love. If the type of reward didn't have any effect, then out of the 44 cats that learned to line dance, half of them should be there and half of them should be there. So that's the 22 that we have there and the 22 that we have there. In a similar way, we should have that the 36 that couldn't line dance after a week, that half of them received food and half of them received love. Let me repeat. We have 80 cats, and in our experimental design, 40 of those cats were given food and 40 of them were blessed with love. So half there, 40-40. If there is no dependence on reward for the ability to learn to line dance, then the 44 that actually learned to line dance, half of them should be under food and half of them should be under love. So it should be an equal split of 22 and 22. And the same thing here. It should be 18 and 18, adding up to 36. So what is given here for us in red is the counts we would expect if we had independence. Let me say that again. The blue are observed counts. The red in brackets, those are the counts we are expecting if we have independence, if reward and line dance are independent from each other. We will be using then the observed counts and these expected counts to do the hypothesis test. We basically compare what we observe with what we expect. So we expect 22 cats, yes, good line dance and receive food. We actually observed slightly more, 28. So we observed more than expected. Under the no year, we expected 18, we only observed 12. So we observed less than expected. And in a similar way, we can compare here and here. But there is a slight problem. If we just look at the differences, here you will see observed minus expected is 6. There it is minus 6. There it is minus 6. There it is. So if we don't want to focus just on one cell, we want to do it for all 4. What will happen is if we just add it together, we get the nice sum of 0. which doesn't really tell us anything. So let me move on and explain what we will be doing. We will be comparing observed with expected, but in a very special way. So the test that we are doing is named the chi-square test. It was developed in the late 1800s by Carl Pearson. So it's also called Pearson's chi-square test for independence. We want to use this hypothesis test to test whether type of reward and learning to line dance are independent. In an hypothesis test, you have a null hypothesis and an alternative hypothesis. And whenever you do a test for independence, always, but always under the null hypothesis, you put your independence. And then dependence will be under the alternative. So always, always for testing for independence, we assume that the two variables are independent and we are looking for a sample evidence to show us that we could reject the null hypothesis and in fact we do have dependence. So null hypothesis, independence, alternative dependence. And as I've mentioned already, we will be doing the hypothesis test by comparing what we've observed with what we expect, and the expected counts are obtained under the null hypothesis, under independence. So the observed counts we can denote with capital letter O, where we have, in our case, 4 cells. So I will be 1 or 2. We have 2 rows. J will be also 1 or 2. We have 2 columns. So O11 would be 28. O12, that is equal to 12. And likewise, you have other 2 observed frequencies. The expected counts, those are obtained with this very simple formula. And in fact, you don't even have to do this calculation yourself in Python. Python will give you the expected counts. You have to give the observed counts to Python. And if you use the function correctly for testing for independence, it will give back to you, Python, kindly, the expected counts as well. But I mean, the formula for the expected counts is basically you take the row total, times it with the column total, and divide by your sample size, in our case, sample size 80. So for example, it was very basic and easy here because I've made the numbers nice, but in general, you would be saying, if I want to get to that 22, it would be 40 times 44 divided by 80. That will give me the 22. And it's the same way for all the other combinations of rows and columns. So maybe as this one as an example there, I would be saying 40 times 36 divided by 80. In our example, it happens very nice values that we are getting because I carefully selected the total there, and these two, I made it 40 and 40, half of it, so that it is easy to understand. Of course, in observed data, it will not always be so nice, the expected counts that you're getting. But yeah. How do we then use the observed and the expected counts? We get a test statistic, and it's called chi-square test. So that is the Greek letter chi, that is squared. And this test statistic is calculated by considering each pair of observed and expected counts, but not just taking the difference. We want to eliminate the effect of the sign, so we square the difference. We say observed minus expected squared. We will, for example, say 28 minus 22 squared. Here we will say 12 minus 18 squared. We don't want the fact that it's now negative to have an impact. So you take squared differences, and then you divide by the expected counts for each cell. This is, you can think of this as a standardization technique used. You basically standardized this squared difference by dividing by the expected count. So this is the formula for the test statistic. Under the null hypothesis, this test statistic has a statistical distribution, which is known as the chi-square distribution, which, because this is now not a statistics module that we are presenting, I'm not going to go as in statistics course at university, but just one day within a summer school program. I'm not going to spend time here talking about SpongeBob SquarePants and chi-square distribution and comparing it to anything like that. it's fine if you know that there is a statistical distribution available called the chi-square distribution. And basically, this test statistic has that distribution under the null hypothesis, and that distribution gets used. We don't need to bother about that because we get blessed with a p-value in the Python output. So I'm going to show you how we can do this in Python. I have the code in here as well because I wasn't sure if I would be able to get my Python or my Spider to work simultaneously, but it should be working. So let's go, we'll get back to that slide, but let's go see in Spider. So really doing this test is very straightforward. Not so much in commercial software, but software that's open source. Everybody think they can do, that's internet connection, not stable. Looks fine there. Everybody thinks they can improve on already existing packages available in Python or in R or wherever and create their own way of doing things. So there are multiple packages, I think, actually available that could do for you this test. I've decided to basically use, well, we need NumPy to get our observed counts in terms of arrays. So I've used that. And then I will also be using SciP and specifically the stats. And from that, we are going to import just this test. This is actually the test function we will be using. Okay, so let me start running here at the top. Import that. Also import that function. So here I've imported the whole package. Here I'm just importing the function. Then I'm going to call my table just CT, and I'm reading in the observed frequencies. I haven't bothered here now by adding labels or anything like that. It's not necessary. I'm trying to keep things here as straightforward and simple as possible because I'm basically after a p-value. I want to know whether my two variables are dependent or independent. So I'm trying to keep this as simple as possible. So I'm reading in the observed counts into an array through NumPy or NumPy. I've done that. So let me maybe just show you. There's now my CT. It is in there. It's the observed. And then I apply the function on CT. And there is the output given. So the output we get is the test statistic value firstly. That test statistic value that's calculated, I didn't repeat it here, but it's using that formula. So thankfully, we don't have to go and program or from first principles. This function will give you the test statistic value if you are interested in it. Then it might be easier to look at it here. It's the same as what is there. That p-value is what we are interested in. That p-value is what we use to do the hypothesis test. In our scenario, you typically do hypothesis testing at a 1% level or a 5% level or a 10% level. The default is typically 5% that people want to do hypothesis testing. There are some applications, so say in the medicine fields where I don't think 5% is quite appropriate, where you want to be more certain, then you might go to 1% or even something more than that. But in our case, if we look at this p-value, it is small. It's smaller than 0.05. And therefore, we can say that we reject our null hypothesis at a 5% significance level. And our conclusion, therefore, is that the type of reward and learning to line dance are indeed dependent. These two variables do depend on each other. Here you can see the expected frequencies or the expected counts given. So that's part of the output given by this function. That DOF or DOF, that's degrees of freedom. One that is linked to our chi-square distribution. To be blatantly honest, that's for us not really here important. You don't need to do anything with that one. You might want to know about the expected counts of frequency. So that's given to us. And then what is important, because our conclusion is based on it, p-value. And yeah, any questions about what we have here?
Okay, so there's questions in the Slack.
Yeah.
So the first one, shouldn't we have another group with no reward in order to conclude that the cats can only line dance depending on the reward?
Okay, so let me think carefully. Should we not have another group
with no reward?
You could do that. I mean, this is not how this example was set up. But yeah, I guess if you want to repeat a study like this, it would be, I guess, a good idea to, apart from just looking at these two type of rewards, you can have an extra level within your category. Yeah. So again, and this is how it is in that textbook as well. On purpose, I've picked now an example where each variable has only two levels. So it's a 2x2 contingency table that we have here. I will first answer the question.
Kurs.
And then I have for everybody a little exercise to work through and see if they can do it. Where you will see, this is from the Titanic. This has two levels, but here we have more than two levels. So yeah, definitely, I mean, this is a very basic example. It was decided food and love as reward. But yeah, you could have a third one in there, which would be reward nothing. So yeah. And then you have to decide, of course, if suppose you have your 80 cats, how you now decide how many will get nothing and how many food, how many love, how you.
Yeah.
Yeah.
Then the next question, what's the difference between testing for independence and sensitivity? Is there a difference?
Yes, there is. But now I must be careful how I try and answer that because I don't want to cause confusion. So when you test for independence, you are testing whether there is a relation between two variables, like what we've done here. Sensitivity, as I understand it, is, and that's what I say, I want to be very careful how I apply to this now, because it also depends in what research field you talk about sensitivity. It's not something that I have done myself really a lot of. I've done a lot of tests for independence, but sensitivity analysis is not a field of research that I have entered into a lot. But that would be where you actually, I don't want to use the word limit, but you put like, you have like a measure from, and if you go beyond that measure, you say that there is impact between. And I'm very careful how I choose my words now. Yeah. So I don't know if I want to go into too much detail about sensitivity analysis here. Might be that we then go on a side track that we can't get back from. So, yeah.
Then there's another question.
Yeah.
What does the 6.111 mean? That's the first number that I put maybe.
Okay, yeah. So let me show you that. You see they label it as your statistic. That is your test statistic value. So what Python kindly do for us, we don't have to do it ourselves. It makes use of this formula, and that's built into the function, into the background. It takes the observed counts. It calculates for us these expected counts. So that's why they can also give it there for us. It compares the square differences between observed and expected, and then standardized by dividing by each cell's expected. And it works out that answer 6 point many ones. That is the test statistic value. Now, in the previous millennium, when computers were not so prevalent in statistical analysis as it's now, you would be asked to go and compare this statistic, test statistic value, with what was labeled a critical value. And in the type of test we are doing here, you would say, okay, I would be rejected when this value becomes large. Because if this value becomes large, what it implies, I have large differences between what I'm observing and what I'm expecting. So if these are becoming large, then clearly there must be some dependence if there's a difference between what I expect under the null hypothesis, but what I actually observe. So also, I didn't mention that. Notice the statistic is a chi-square. You cannot get negative test statistic values here. So your test statistic value can only be positive. And if there are large differences in any cells or all cells or most of the cells, but when you start seeing those differences, then this test statistics value becomes inflated, becomes larger. So what you would have to do then is you can go and compare this test statistic value with what they call a critical value. And if your test statistic value is more than that critical value, that for this test comes from a chi-square table, then you reject the null hypothesis. So some other hypothesis tests, you don't use the chi-square distribution, you use the normal distribution. You would be comparing a test statistic value with a Z value from the normal distribution. So that is how, I remember when I was taught statistics many, many years ago, we had to compare test statistic values with critical values. And that was difficult enough for us. And then if you were not happy when you got the next question, go and calculate the p-value, because you actually had to read all these off from tables. It wasn't done by computer. Nowadays with software, they still give you the test statistic value. That's basically standard, whether you're working in Python or R or in SAS or Starter. They will give you a test statistic value. But we don't really have to go and find a table for the chi-square distribution and compare this now with a table. We don't need to do that. I don't know why that's appearing here. We should not have done what I did. It's basically, we can just use the p-value that we are given. And for the p-value, it's a straightforward rule of thumb. You reject the p-value when you reject the null hypothesis when the p-value is small. And in our case, small is, we say, well, it's less than 5%. We can reject at a 5% level of significance. We could not reject at a 1% level here because this is more or greater than 0.01. So it's not that we would be able to reject at a 1% significance level.
There's another question. How can we change the 5% significance level to something else? Maybe just one.
So as I said now, and I've made it 5% because this is sort of the default, but notice nowhere here they specify for you the significance level in there. They go and calculate the p-value. That's the beauty of a p-value, that with a p-value, you don't need to beforehand specify the significance level. Whereas if you compare a test statistic value with a critical value, that critical value depends on whether you want to test at a 1% level or a 5% level or a 10% level. That is not a concern when you work with a p-value. You simply say, I reject if my p-value is small. And the nice thing of it, you can interpret it immediately by saying, oh, I can reject at a 5% level. Or, oh, I cannot reject at a 1% level. So suppose my p-value was 0.07, then I would say, oh, I cannot reject at a 5% level, but I can reject at a 10% level. And that might be fine for you within your field of research to be able to reject at a 10% level. As I mentioned earlier, in medicine or, say, pharmaceutical companies, I don't think they want to be only rejecting at a 5% level. They might be, well, that is not strong enough evidence. They might want to test at a 1% level, and the result like this would then not be acceptable for them. They will say, well, I cannot reject the null hypothesis. And if they don't reject, then the conclusion would not be dependence, but independence. So within your field of research, you will typically be guided by what your significance level should be that you want to test at.
There's one more question.
Yeah, no, it's fine. Please have one question so that I can try and find answers.
So I'm not 100% sure what it means, but is 5% rejection a stable value if p-value is greater than 0.05? I think you might have touched on it in the previous discussion.
Yeah. So as I've mentioned here now, my p-value was 0.0134, so it's less than 5%, so I reject. Suppose my p-value was not this, but my p-value was 0.08. Then I cannot reject at a 5%. And then I could, but the conclusion would be correct if I say type of reward and learning to line dance are independent. I couldn't reject the null hypothesis. However, if I am willing to test at a 10% level, then because my p-value is 0.08 less than 10%, 0.1, then you could then say I reject. If you're willing to do that, reject at a 10% level, and then you could say your conclusion is that the two variables are dependent. I must be honest, the standard way of doing hypothesis testing always have been 1%, 5%, or 10%. I struggle to see really the merit for 10%, to be honest. But it is still unacceptable. I don't think you're going to test really in the other level. It's not that you will say, I'm rejecting a null hypothesis. I will not say I'm rejecting at a 2% level. It just sounds funny to say I'm rejecting at a 2% level. Yes, it's less than 0.02, but that complicates now matters, especially when you deal with people that need to read your research that are maybe not so well versed with numerical values. I'm not even talking about statistics, but yeah, that find that difficult to comprehend. So when you're going to do a hypothesis test, when you do research, you will typically test 1%, 5%, maybe 10%.
Okay. The question that just came in.
Yeah.
You did touch on it previously, but maybe you can just repeat. What do the parameters, statistic, p-value, DOF, and expected frequency mean in the output?
Okay. So this statistic is the test statistic value. It is that value is obtained if you take each observed count, you subtract from that observed count the corresponding expected count under the null hypothesis, square that difference and divide by expected count. And all of those get summed. So there is a double sum because you do it over the rows and the columns. So you do it for each of these cells. So if you do that, if you got, for those of you that have the time and energy, nothing better to do this coming Friday evening, if you want to go and do that, you can type in these, work out the differences, square them, divide by, you should be getting the 6.11. That's the test statistic value. The p-value is what we base our hypothesis test on, our conclusion and our decision. We decide whether we reject or not by comparing this with a significance level 1%, or in my case, I used 5%. DOF is the degrees of freedom. That's linked to the chi-square distribution. We don't need that. For those that wonder, the reason why it's 1, it's row minus 1 times number of rows minus 1 times number of columns minus 1. We have 2 rows and 2 columns. So 2 minus 1 times 2 minus 1 is 1 times 1 is 1. But yeah, we don't need to use that one anyway. And then the expected frequencies or the expected counts, those are now the expected counts that I've put in there in red. So that is under the null hypothesis of independence, what we expect to see. Blue is observed and the red there is expected. So again, this function in its result give us these expected counts. We don't need to go and work it out ourselves. I did give the formula here of how it's done, but we don't need to do that. So what is the time, Rene?
It's 4 o'clock, almost 4.
Right.
There's 2 more questions.
Oh, there's more questions. Okay, no, that's fine.
In.
Yes, okay.
Okay, so the one I think you did touch on, but maybe you can just repeat. What are the risks of having higher significance level values? Say 15% instead of 5%.
Yeah, so typically by default, you're not going to, as I said, you're going to use either 1%, 5%, or 10%. I cannot see that you would want to use 15% or 20%. So I would not want to have a hypothesis test where I make a decision based on, say, 10% really, because if you think about it now, if I say I am rejecting the null hypothesis at a 10% level, then what you're basically saying is that, and I need to be again careful because I don't want to go too much into the theory about what is a type 1 error and a type 2 error that can be made. But maybe mention that. So when you do hypothesis testing, you have a null and alternative hypothesis that you specify. And there's two types of errors you can make when doing a hypothesis test. You could be rejecting a null hypothesis that is actually true. So the null hypothesis is true, and you are rejecting the null hypothesis. So that's the one type of error that you can make. And the other error you can make is that you should be rejecting the null hypothesis and you are not rejecting the null hypothesis. So you're incorrectly not rejecting a false null hypothesis. We control in hypothesis testing the first error I referred to. So that's referred to as the type 1 error that you can make, that you are incorrectly rejecting a true null hypothesis. And we fix that probability of making that error, and that is the significance level. We fix that as, say, 10%. So if I am saying I reject at a 5% significance level, for example, what I'm saying is the probability that I'm incorrectly rejecting a true null hypothesis, that is 0.05. I fixed that. If I make that 10%, I'm increasing the probability of incorrectly not rejecting that false null hypothesis. I'm increasing that probability. So I want to have that my significance level small. I don't want a large significance level. And that's what I'm saying. Typically in practice, it's made 1% or 5%, sometimes 10%. But I find that nowadays it's more of a textbook thing of helping explain, oh, you can also test at a 10% level. But it's not, I cannot really think of a research field where you want to be commenting on rejections at 10% level. Yeah, I would not think that is really appropriate. You said there's another question, Rene?
Oh, yeah, that's quite an interesting.
No.
Okay, but yeah, maybe you can just comment. Not sure whether this is the time to ask.
Yeah.
If the sample size is relatively small,
yeah,
for example, a natural phenomenon that occurs only 7 out of 5 years, then significance is always going to be problematic, in my opinion. What to do then?
That is correct. So in doing hypothesis testing, you need to be careful how you apply it. So I did not look here at a scenario where we only had 8 cats. We had 80 cats, which is a lot. I don't know where you find 80 cats. Yeah, I don't know how and why. I mean, I have one, well, no, actually 2 cats that's bothering me where I'm living. It's not my cats, it's neighbors' cats that think that our garden is a nicer place to visit than their own garden. Well, okay. So at the bottom, that's why I have a python also to try and keep it away. But yeah, to get back to, yeah, of course, when you have smaller numbers, then you start running into problems. In fact, and I didn't mention it anywhere here, but I will mention it now. In doing chi-square independence, there's actually a rule that in your cells, all your expected counts should be at least 5. So if you have expected counts less than 5, then it becomes problematic. You can still perform the test, but you should be careful about conclusions that you make based on the test. Here we are far more than 5 in all 4 cells. But you can imagine, on the one hand, what could happen? You could have fewer numbers. So you didn't use 80 cats, but you maybe only use, say, 20 cats. And you could start running problem. Or you could, as we've mentioned, have not just 2 levels, but maybe you have a 3rd level there, not just food and love, but you also have a level there, no reward, nothing, nada, nux. So, the more levels you have, also the more spread out your counts become across the various cells, and that also can have an impact. So indeed, when you have small numbers, there are other tests available. So I've done now here Pearson's chi-square test for independence. There is another test available by Fisher's exact test that can be used, but Fisher's exact test, now that I think about it, is only for 2x2 tables. Yeah, it's not applicable. Well, no, it is applicable for others, but it becomes, yeah, the more cells you have, so the more columns or rows you have, computationally becomes very demanding, and you might be sitting and waiting, even if you have a super fast computer, while Python or your software package try to calculate it. On purpose, I decided not to include Fisher's test here, but just do Pearson's test. Yeah. Anything else, Rene, before? So you can actually use my code that I've loaded for you on, well, I didn't upload it there. I had a kind colleague that did it for me. Thanks, Rene. But you can use that code and modify it a bit and see if you can test for this. So we'll give a few minutes time for students to do this exercise maybe quickly. Where it has to do with the 2,201 passengers that wish they never climbed on a ship. Well, that wish they never climbed on the ship called Titanic. And yeah, it's a two-way table again. So we have two variables, but now our first variable, the class on the ship, which is a proxy for the economic status of the passenger, whether it's first class, second class, or third class, or then crew member, and then survival, yes or no. And the question is basically whether the survival of the passengers on the Titanic was independent from their economic status. So see if you can, for this table, get the hypothesis test done. You basically, to do this, you basically need to just here change how you read in there, in your table, the values. So I'm too lazy to now do it there. So I did earlier. So just go and open. So I have to for Titanic, and it's a bit bigger. So only bit of the code that has to change is where you type in this. So just gonna put the code there, and we are given again our test statistic value, which you will see is now much larger here, 190 point something. So the previous example was 6. And notice there the p-value is given a scientific notation. But here we now have an example where the p-value is extremely small. The degrees of freedom 3, That is now again linked to the chi-square distribution, so that's not really of that much importance. And then we have our expected counts that was calculated for each and every cell. So we observed, just to use as an example, we observed, if I go back here, we observed 122 who did not survive, but was first class. That's what we observed. Under independence, we expected it to be 220 that did not survive. Likewise, that is 104, make it 105, that we round to the nearest integer. 105 is what we are expected to have survive. Just see the order, it is first, to survive. Only 105, yet from first class, 203 survived. So we notice that this observed is much smaller than the corresponding expected. Here, the observed is much larger than what's expected. So already we pick up there some differences there. And likewise, we see in the others, I think if I remember correctly, the crew is about the closest we get is in terms of the crew, I think. But there's maybe the difference not that big. Now, even there, it is quite big for the crew. But yeah, because there are differences, we therefore we take these differences, we square them, and even though we divide by these expected counts again, we get a rather large test statistic value, and the corresponding p-value, so this is rather inflated, the corresponding p-value is therefore very, very small. We can comfortably at a 1% level reject the null hypothesis of independence. So your status on that ship, that matters on whether you survived or not. There's a dependency. I don't know if there are any questions about this.
I see someone is typing.
Well, okay. It's just before we get to the forensics. I strongly, well, the question being typed, I mean, cannot say enough. I mean, for many of these things, I had to, because I haven't recently worked in Python. So I had to do a lot of Googling. Please don't be afraid to ask Google if there's something you're not sure about. Even when I do, because most of my coding nowadays I do in R, sometimes Mathematica, not so often as before. Sometimes I have to code in SAS for students. So you see I have there a few statistical things here at the bottom. But yeah, I constantly Google to get answers to things that I don't know. So don't be scared to Google, whether it's in terms of coding or whether there is maybe a part that you don't understand. Now, in the past, many of the answers you were getting for Python, but also for R, was very much just how the function works. But you do now get some websites where they actually go beyond just explaining the code, but actually go into detail of what is happening. They do a proper example and showing you what is the different parts. So if there's something regarding the specific test that you are wondering, yeah.
Okay, a few questions coming in. So the first one says that the survival now depends on the class in this case.
Yes.
So that is.
Yeah.
Then do we have to account for the higher degrees of freedom?
This is done automatically by the hypothesis test. So the degrees of freedom is a parameter within this chi-square distribution, and that gets used internally by the function to work out what is the correct p-value. So it's used in the p-value calculation. That's done for us. No reason for us to worry how that gets done. So yeah, it works together with the chi-square distribution. So it uses the test statistic value, it uses that degrees of freedom, and the chi-square distribution, and that p-value gets calculated for us. We basically, all we need to do is interpret the p-value correctly, make the correct decision, and then the correct conclusion.
Okay, the next question is, my hypothesis is that more members survived.
Well, we need to be very careful now. What we've tested here, and I didn't write it out anywhere, so I will only be able to say it. Our test is, well, like we had it there, we said here, we test independence versus dependence. And the same thing is happening here. We test the null hypothesis of independence between the two variables against alternative dependence. We are observing, for example, that more crew members say here than expected, or fewer crew members. Yeah, I can't remember now. Let me go and see the expected. Is it? Oh, it's more. More crew members that did not survive than what we expected, but we are not testing specifically just for the crew members or just for those in second class. We are testing this variable class with 4 levels against this variable survival with 2 levels. We can go and, given that we've rejected, we can go and compare specifically individual cells observed with versus expected. But for the hypothesis test of independence, it's based on the whole table. So in this case, all 8 cells that we have. We are not testing crew versus survival, or testing first class versus.
There's someone that says he got slightly different values. Can you maybe go back to the code?
Well, maybe I did something wrong. Maybe I typed in wrongly. It could very well be that I made a mistake when I typed in here.
He has 188. You have 118.
Okay, so I made a mistake. Okay.
No, let's just.
I have to make, yeah, well, I have to make at least one mistake today.
No, yours is 118. So yours is correct. Okay, so he's. I'll reply to him.
Okay, we will. Okay. Okay, so it's just maybe one of the cells. I see there's a 118, but there's also 178. Okay. Ah, damn, I was so hoping that this was now my mistake for the day. So I still have to wait for. Okay. Let us then move on from independence testing to now I don't have that because I didn't download it. But I can get it from here. I will quickly just Google it in here. Because I just want to show students where they can read more. So data 8 is famous from the University of UC Berkeley on data science that they present there to their students. So you see these are fall and spring is their terms, and they use Python. So that's nice for those of you that fell in love with Python. But I want to quickly get to the, so not here where I want to be, I want to get to the book. The textbook, the one that was earlier, right at the beginning, that Rene mentioned. So this is the book. So it's a nice book if you want to read more about certain parts of statistics. There's no way that we could be doing all of this in a single day. So we've selected parts of what we thought might be of interest and useful for you. The next bit I'm going to have a look at is what they refer to as updating predictions. So under this updating predictions, there is the last chapter there, more than likely than not binary classifier and making decisions. So for more reference about what I'm going to do next, you are more welcome to go and read the examples they do here. I won't say it's boring examples. I've seen worse from US textbooks. about jury theory, jury duty, and things like that. There's not a bad example, and they do explain quite well, I think, here what's happening. Why I mentioned this is we're going to talk about Bayes' rule now and what we're going to do next. And Bayes' rule has become widely used, as I mentioned there. His method, it is not a new method, but it's now widely used in machine learning. That I think you've already done a bit of machine learning this week, to the best of my knowledge. So that's why I've decided I think this is something we can have a next look at. So we're going to go back to probability theory. And along with that, we will be looking at something called tree diagram. Now, to the best of my knowledge, there's no nice package available in Python to draw tree diagrams. So the tree diagram I'm going to show you, this was not drawn in Python. I'm pretty sure about it. I don't know what they've used. I'm going to show you also tree diagrams, or a tree diagram and what I'm going to show you. But yeah, I did not draw that with Python. So just a disclaimer, the plot you will be seeing was not done. So in fact, we're not going to really need to work in Python unless we want to use it like a calculator, but we're not going to run packages and stuff now. So let me get to this. So tree diagrams and Bayes' rule. So this is an example that I've conjured up. So none of the probabilities we're going to see are in this example are true probabilities. It's sort of made up. It is based on a project that I collaborated on quite a few years ago that was rather controversial. So it is with a colleague of mine from forensic pathology. He's actually a dentist and a forensic odontologist, world famous Professor Herman Burnage. And he might be retired now, but he would come in on a weekly basis from where he stays in Mpumalanga to the University of Pretoria to give some classes. Sometimes he needed to meet with me. I did the statistical consultation work for him and helped him with some of his projects. But also, yeah, he would go to the mortuary to do not too nice things. So I often tell my students that I'm so glad that as a statistician, I don't really have to do data collection. I am given data sets to work with, but I don't need to go and do investigations of burnt bodies, for example, which this is about. So I think it was mentioned in the right at the beginning that, yeah, I've worked on some forensic pathology problems. And this particular one is a very, very interesting one. There's a big debate still raging about this. And a lot of it is based on the ideas of Professor Burnage. So he's an expert on identifying people through teeth, because he's also a dentist and a forensic odontologist. And what he would happen, unfortunately, quite a few people in South Africa die. Either they die because of fire, or they were already dead, and then there's a fire used to get rid of the body for whatever strange reason. So it would happen that there might be a car accident and then there's a fire, or there's a veld fire, but there's a body found, and he's called in as the pathologist, and then he has to do whatever pathologists do to try and identify the body. So it's a victim that needs to be recognized. And what he picked up, interestingly, was that when he got to the corpse, sometimes the tongue would be sticking out, or the official term, it would be protruding, and sometimes not. And he would, for example, he explained to me once he was sent to a helicopter crash into a mountain. And the two front passengers, their tongues were not sticking out, so those in the front seat, but those in the back seat, their tongues were sticking out. So what could be the reason? Well, the two in the front died on impact as the helicopter crashed into the mountain. There was then a fire. The two in the back seat were still alive, and they were trapped in the helicopter and unfortunately burned to death. And as they were trying to breathe, what happens is the tongue was protruding out, they were basically trying to breathe. So he has this hypothesis then, Professor Burnage, that to identify whether, when there's a body, whether that victim was exposed to the fire before or after death, and this is very important in court cases, to know whether it was maybe somebody that was killed and then tried to get rid of the body, or whether it was an accident, so that it's referred to in pathology as vital burning, and in court cases. There are ways of detecting it. The most popular way of still doing it is to basically, on the examination table, cut open and check whether there is soot present in the respiratory tract and stomach of the victim. So that is considered the indicator of vital burning. Vital burning, the person was alive and burned to death, and it's called vital burning. So that person, by breathing in soot into the tract and then into the stomach, yeah, that is the indicator of vital burning. So in this article, the proposal was then that tongue protrusion could also be used as not the indicator of vital burning, but an additional indicator. Why? It's a very easy thing to do. To check for soot, you have to, well, have a pathologist work on the body. The person, say a policeman or police lady that first appear on the scene as in terms of authority, they can immediately see, or notice there, the tongue is sticking out. This is an indicator of potentially vital burning. So a lot of controversy this article caused. A lot of people from all over the world commented on the article, tried to prove or disprove it. So it has caused a lot of debate in legal medicine and in forensic pathology, whether the tongue protrusion can be used or not. Also in terms of the physiology, of which I don't know a lot. But yeah. So this is the scenario that's now pictured for us. And as I said, these percentages we're going to see is made up. So figment of Paul van Staden's imagination. These are not real. It doesn't come even from this article. We didn't do what I'm doing here in the article. In the article, we did other things. But yeah. So suppose it's known that 84% of burn victims have soot present. That is our first knowledge that we have available. Then we are told of those burnt victims with soot present, 75% have protruded tongues. So you should already picking it up here from what we did before, the way this sentence is structured, that this is a conditional probability that we are given here. Given that soot is present, the probability of having a protruded tongue is 0.75. The second part of the sentence, only 12.5% of the burn victims without soot present have protruded tongues. So given that soot is not present, the probability of having the tongue protruded is 12.5%. And then we are told a burn victim is now randomly selected. Given that this victim has a protruded tongue, what is the probability that the victim will have soot in the respiratory tract and stomach? So the way this gets painted to us is, we know, based, say, on historical data or given by Paul van Staden, whatever way, subjectively, not objectively, let's say 84% of burn victims have soot present. That is known to us. We know this probability. Given that soot is present, the probability of a protruded tongue is 0.75. Given soot not present, the probability of protruded tongue 0.125. So we have those two. But this is not how a victim is presented to the pathologist or the people. I mean, they don't know soot is present and then have a look at the tongue. Actually, it's the other way around. You're first going to notice whether the tongue is protruded or not before you're going to start working on the burnt victim body and start cutting up and doing all kinds of forensic fun and games. So the other way around is actually what we want. We want to, well, given that the victim has a protruded tongue, what is now the probability that soot will be present? So that is what we want to work out. So here I've summarized what was in a lot of words, I've tried to summarize it here now in terms of probability notation. And to prevent slides that are as boring as this, on my screen, it is deep pink. On the screen that the people present here at University of Victoria are looking at look more like passion purple. But yeah, to avoid single colors, I've added some other things. So yeah, I know forensics is one of the research fields that have been romanticized by television programs. So many first or potential first-year student pitch up at open days at universities wanting to become pathologists. And Professor Burnage told me that it's quite an interesting discussion to be had with these potential students to explain to them that what you see on a CSI or on a Bones or whatever, or there's so many of these programs, real life is not that nice to be working in pathology. But yeah, so I've decided to just add for some color here. But yeah, this is actually what we need to focus on. We have two events. Event A, suit present. So immediately we have a complement, suit not present. It's either one of the two. Suit is present or suit is not present. And then we have an event B, tongue is sticking out. So tongue protruded or tongue not protruding, tongue not visible. And these are the probabilities that were given in a lot of words here. So probability of A is 0.84, the probability of suit presence. Given that A occurs, so given suit presence, the probability of the tongue protruding is 0.75. Given that the tongue, that suit is not present, the probability of the tongue protruding is 0.125. We want to calculate this probability. This is what we want to calculate. The probability of A given B. Given that the tongue is protruding, so given B, what is the probability of A? So that's what we want to calculate. And earlier on in our first example that I did with earlier, I talked about the conditional probability rule that says, well, this probability is the probability of A and B, so the intercept, divided by the probability of the one that's given. So divided by the probability of B. We don't have this available. We don't know the probability of A and B. We also don't know the probability of B. We will be able to calculate it, but we're not given these two probabilities. So we need to first calculate these in order to be able to calculate this conditional probability. So just why I say we need to do this, let me just go earlier where I showed that if you want the probability of A given B, it's the probability of the intercept divided by the probability of the one that's given. Not these frequencies, of course. That's not applicable now. Okay. So first we want to get the probability that a randomly selected burnt victim has suit present and a protruding tongue. We can get this probability by using what was given to us. We were given the probability of A is 0.84, and we were given the probability of B given A is 0.75. Now, this probability equals the probability of the intercept, B and A, or A and B, doesn't matter which way around, but the probability of the intercept divided by the probability of the one that's given. We have the probability of A. So we want this probability. So by rearranging, we could say, okay, if this probability is this one divided by this one, then we can get this by saying this probability multiplied by this probability. So we can say 0.84 times 0.75. That is 0.63. That is the probability that a randomly selected burn victim has suit present and a tongue protruding, 0.63. In a similar way, using the information here, we can calculate these other three probabilities as well. Where the first one I have there is A complement and B, which would then be the probability of A complement times the probability of B given A complement. This probability is 0.16. because soot is present or it's not present. So if probability is A is 0.84, then the probability of A complement is 0.16. And this probability we were given, probability of B given A complement 0.125. So we can work out the probability of soot not present and a ton protruding. We can work out the probability of soot present and the ton not protruding. It would be the probability of that one times the probability of B complement given A. Again, we have that probability. We have that probability. Well, we have this probability not given here, but let me explain that. Soot is present. We say that happens. Then either the ton is protruded or not. So if soot is present, the probability of B is 0.75. Therefore, if soot is present, the probability of B complement is 1 minus that. So 0.25. So that's where that comes from. And in a similar way, the one that we have there is 0.875. If soot is not present, then either the ton is protruding or the ton is not protruding. So that one plus that one must also add up to 1. And the best way of showing this is actually through a tree diagram. So this diagram that we have here is labeled a tree diagram, which shows us these various probabilities and the extra ones that was calculated. So the first branch is in terms of soot presence. Yes or no. We were told this is 0.84. Therefore, this must be 0.16. These two must add up to 1. Given that soot is present, we then have the ton protruding or the ton not protruding. So this one was given to us. Let me just go up there. We were given that this is 0.75. Therefore, this must be 0.25. This must add up to 1. And the same thing happening here. We were given this 0.125. This is now soot not present. Given soot not present, what is the probability that the ton is then protruded? Well, that one must be then 1 minus that, so 0.875. So this adds up to 1, this adds up to 1, and this adds up to 1. And then to get these at the end, and these are now probability of soot presence and ton protrusion, for example. Yes and yes. This is the probability. Yes and no. You basically say this one times this one gives you this. Or this one times this one gives us this. And the same for the other two. And this is how we can work out these probabilities that we have here, the intersect. We need particularly this one and this one. Now, Rene, there must be questions or not? Are there questions? Or not yet?
One was just about the scenario. How did the person die before being exposed to the fire? But nothing on the probability.
Okay, now that we don't know, luckily. We were not told this poor randomly selected burn victim. We don't know. It's just a randomly selected burn victim, yeah. All that we have available information is what was given, this kind of information. We don't have extra information now. Obviously, for a burn victim, you're going to see how the ton is protruded. So we could see that. We want to know what is the probability before we start cutting up the victim that they will be soot in the respiratory tract. But we don't know if it was a felt fire, whether it was a car accident, whether it was a fire now, whatever. We don't know. It's not known for us. Okay. Any questions about the tree diagram? Any part of the tree diagram?
I don't see any questions. I don't know if someone is typing.
But okay. While we wait, I will continue to just explain. Remember what it is that we want to calculate. We want to calculate the probability of A given B. And we've said to do so, we need the probability of A and B that we've calculated. We have that available, 0.63. We also need the probability of B. We want the probability of a ton protruding. Now, this is where people need to be careful. I've seen many times what then happens is people say 0.75 plus 0.125. There's a yes there, there's a yes there. We do not add this to this because this is not the probability of tunnel protrusion there and the probability of tunnel protrusion. This second branch is conditional upon what happened there. There's a yes, given yes, what is the probability of the tunnel protrusion? Or given no, what is the probability of the tunnel protrusion? So we do not add this one to this one. We take the 0.63 and we add the 0.02. And this is known in probability theory as the law of total probability, which is basically, if I want the probability of B, I take the probability of A and B plus the probability of A complement and B. So please note, I don't add up all four. If you add up all four, you're actually going to get 1. 0.63 plus 0.21 plus 0.02 plus 0.14. That gives you 1. Because these are the 4 potential scenarios that we have. Suit present, yes, no. Tunnel protrusion, yes, no. We get 4 possible scenarios. For probability of tunnel protrusion, we go to our branches where we have a yes there and a yes there, but we don't add this and this. We take this one and this one. And the answer is 0.65. So probability of B is the probability of A and B plus the probability of A complement and B. So the and B is important because we want B, and then it's A and B or it's A complement and B. Suit present and tunnel protruding or suit not present and tunnel protruding. So we add that, we get 0.65. And then because we have this and we have this, we can go and work out the probability that we want. Given that the randomly selected burn victim has a protruded tongue, the probability that the victim will have suit present is this ratio. It's probability of A and B divided by the probability of B. And that is actually quite high. We see here, 0.97. And all these calculations now, there's no package to run in Python. There's no functions to run for this. You can work these out, of course, by using Python as a calculator. So for those that are interested in, I formulated a similar problem, but instead of focusing on tunnel protrusion, I used another method here that they do for vital burning, and that is looking at the blood level percentage for COHB, carboxyhemoglobin, which I will not say again because it is a terrible word to say. Specifically in the world of forensics, a high blood level percentage of greater or equal to 10%. That's what they consider high. It's more than that. Then it is indicative of vital burning. So I've kept that as 84%. So that's the same as what we had here, 84%. But I've changed now, different from tunnel protrusion. I've made it 95% and 65%. Here it was, let's go and see, 75% and 12.5%. So you're welcome on your own to go and work out what is, given that this occurs, what is the probability that the victim will have suit present. So you can work it out. Leave it for you. What is the time, Rene? Is it lunchtime? Yeah, so, but I will answer questions if there are questions.
I see that according to the program, we are back at 2.
Yes, yes.
Because it's lunch break and then a guest.
Yes, there's a guest. I don't know if there's a guest speaking today, but
yeah, they said that.
Is there a guest? Okay, so there's a quarter to guest talk. Okay.
But I don't see any questions.
Okay.
There's no one typing.
Okay. But okay, then we can take lunch. And then we will be back at 2 o'clock. Yes.
Thanks, Prof. Yeah, so thanks, we can have a lunch break. Thank you. We can have a lunch break now. at 1.
I promise
So
the next example will not be so gory. It will be scary, but not so bad. Yeah.
Hello? Thank you. We're going to have a guest talk at 13:45. We should be back by 13:45. Thank you.
Waar gaan jullie niet?
Ja.